that time begins the Yuga and the synodic month of Magha, solar month called Tapas, bright fortnight called Magha, and the northward course Uttarayana. So winter solstice is beginning of the asterism. Winter solstice for that time, Delphini Savishta segment. This corresponds to some time between 1370 BC and 1150 BC. You see, there is a precession of equinox, right? So because of that, the winter solstice and summer solstice and equinox, they change their positions. So the winter solstice, if it was there near Shravishta, so then it was nearly 1200 BC. The whole calendar is summarized like this. 366 days form the solar year. In the year, there are 6 Rutus and 2 Ayanas, that is northward and southward quarters of the sun. There are 12 solar months in the year, and 5 years make a Yuga. So there's a short Yuga. So in a Yuga of 5 years, there are 60 solar months of 30.5 days each, 62 lunar months, and 67 sidereal months. So this is what it says. Vedanga Jyotisha of Lagada, around 1200 BC, you can say. So the Vedanga Jyotisha calendar, you see, it has, in a year, in a Yuga, there are 60 solar months, 62 lunar months, 67 sidereal months, and 60 into 30.5, 1830 civil days. So a sidereal year is 1830 by 5, that is 366 days. Actually 365.2564 days. Okay, sidereal means sun coming back to the same position in the space, not to the equinox, not equinox to equinox. That will be little less. That will be little less than 365.25. These are little more. A lunar month is 29.516 days. Actually, is 29.5306. A sidereal month is 27.301 days, and actually is 27.321 days. So there are 60 solar months and 62 lunar months in 5 years. So there are 2 Adhika Masas in this period, okay? So the 2 more lunar months. So you have 3 lunar years with 12 months and 2 lunar years with 13 months in a Yuga of just 5 years. So the concept of Adhika Masa, what we call intercalary months, we have it now. Even now we follow. All this was there, long back. And many of the features are also even now followed. But here the motion of the sun and moon in the background of stars is uniform. Okay? So there is no change in the duration of a month or a day or a solar month, lunar month and all that. But we know that changes. And what we call a civil day, 24 hours, is actually the average of sunrise to sunrise. And what we call a lunar month, which is 29.53059 days, is actually average of all lunar months. Similarly, the concept of Tithi is mentioned in Vedanga Jyotisha for the first time. Tithi is 1/30th of a lunar month. So 15 Tithis in each Parva are half of a lunar month. So there are short algorithms for finding Tithi, Nakshatra, sun's position in the sky, etc. And very importantly, significantly, the duration of the day. What I mean is sunrise to sunset. The daytime, when sunlight is there, it varies over the year in Vedanga Jyotisha. Okay, so that is and it gives a formula. It gives a formula for that, which corresponds to 28 degrees, approximately 28 degrees. You see, in Bangalore or Chennai, the variation of the duration of the day is not too much. Our latitude is only around 11 degrees. But if you go to north, you might have seen, okay, that sometimes, in the winter, sun will set at 5 o'clock. And sun will, rise in the next morning at around 7 o'clock, like that. Or if you go even, if you have gone to Europe and America and all that, not more northern latitudes. In fact, when I first went to Italy, I was shocked, because sunlight was there at 9 o'clock in the night. So that is because of the latitude, higher latitude. So that depends upon the latitude. So what this corresponds to, it gives the formula, it corresponds to 28 degrees. So this is the first text in India to give mathematical algorithms. So that means rules. See, to find out when the sun or moon is in a different nakshatra and where it is in the path and things like that. And we still, the sutra format, giving rules, that is still followed in Indian astronomy. There is nothing on planetary motion in this work. So it is mathematical astronomy, but little limited, right? It's arithmetical astronomy. Arithmetic, because as we will see shortly, for full mathematical treatment, we need trigonometry. Okay. So after this, there is the Siddhanta period. True mathematical astronomy begins with Aryabhatta, Aryabhatiya of Aryabhatta in 499 CE. And this is the first discovered Siddhanta text in India. So there's a long gap between Vedanga Jyotisha and Aryabhatiya. And during the intervening period, there are books with passages related to astronomy, like Buddhist text called Shardula Karanavadana, Jain text Chandra Pragnapti, Surya Pragnapti, and also you would have heard of the famous Kautilya's Arthashastra. There are some passages related to astronomy, the time relation between shadow and time, and so on and so forth. Now, according to tradition, there were 18 Siddhantas before Aryabhatiya. 5 of them are summarized in what is known as the Pancha Siddhantika of Arakmira. Pancha means 5, as you know. So they are Paitamaha, Vasistha, Romaka, Paulisha, and Sauras Siddhantas. These deal with the various astronomical problems associated with motion of sun and moon, including the true motion, I will come to that true motion, diurnal problems, lunar and solar eclipses, motion of Staragraha, that is Mercury, Venus, Mars, Jupiter, and Saturn. Saura Siddhanta is the most advanced. And actually, this Pancha Siddhantika is early 6th century after Aryabhatiya. And in Saura Siddhanta also there is what is known as the epicycle theory for these objects with 2 kinds of corrections, which is the essential ingredient of planetary theory of Aryabhatiya and all later Indian texts. Quite a bit of trigonometry is there in Saura Siddhanta. So these are here summarizing the tradition before Aryabhatiya. So this was, all these things are there before Aryabhata. But though this text itself is little after Aryabhata. Now, is composed after the Aryabhatiya. In fact, Varaha Mihira mentions Aryabhata's name in his work. It is possible that he was influenced by Aryabhata's works. Okay. So, as I said, our earlier available text is Aryabhatiya deals with the traditional astronomical problems. And it is mentioned in the text itself that it was composed 3,600 years after the beginning of Kali Yuga, because Kali Yuga beginning is supposed to be 3102 BC, the 12 o'clock night in between February 17 and 18, 3102 BC. So that's the beginning of Kali Yuga. So Aryabhata says he is composed this 3,600 years after that. So it is 499 CE, and that he was 23 at the time of composition. So he composed the work in Kusumapura, which is the same as Pataliputra, which is all, ancient town near Patna, Bihar, Patna. He has got only 121 stanzas and has 4 parts, namely Gitika Pada, Ganita Pada, Kalakriya Pada, and Gola Pada. 4 parts. Pada means in 1 quarter. So Gitika Pada has only 13 stanzas or shlokas, okay? And there is some correspondence between numbers and letter. So that is there. And this concept of Kalpa and Mahayuga are there. And in a Mahayuga, how many revolution numbers of planets and associated parameters are there? Now, Geetika Pada in 33 stanzas deals with mathematical problems such as, please listen, in 33 slokas, it discusses squaring, square root, cubing, cube root, areas of a triangle, trapezium, general plane figures, volumes of right pyramids and spheres, value of pi, methods for computing science geometrically, constructing a sine table, arithmetic progression, summation of first 10 natural number, that is 1 plus etc. up to n, sum of their sums of squares, that is 1 square plus etc. up to n square, and sum of cubes of first n natural number, that is 1 cube plus 2 cube etc. up to n cube. And what is known as the Kuttaka procedure to solve linear indeterminate equations, relative velocities of moving objects, and even a problem related to interest calculation. Imagine, only in 33 stanzas. So naturally, it only gives a rule, very brief, and later astronomers like Bhaskara 1, mathematician astronomers, they elaborate on this and tell us how to understand the verse. Then Kalakriya Pada in 25 stanzas deals with reckoning of time, calendrical concepts, planetary model, I'll come to that, epicycle and eccentric circle theories, and explicit procedure for calculation of planetary positions. That is very important. I will come to that. Then Gola Pada, Gola, as you know, Gola is a sphere. In 50 stanzas deals with problems of spherical astronomy such as Bhagola. We use that in Kannada also. Bhagola, celestial sphere. Bhugola is, of course, Earth sphere, terrestrial sphere. Bhagola has seen at different latitudes. Daily problems associated with motion of sun, moon, and planets on the celestial sphere. Situation of Earth and its shape. Brightness, darkness of planets. Parallax, lunar eclipse, solar eclipse, and importantly, rotation of the Earth. Aryabhatiya is the first text to say that Earth rotates. It is not that all the planets and all that, sun, moon, rotate daily, stars from east to west. But actually, Earth is rotating from west to east. And what you see is the apparent motion of the celestial objects. Aryabhata has composed one more work called Aryabhata Siddhanta. The manuscripts have not been found. However, some portions of that have been found in some other texts. And it is also a popular work, Aryabhata Siddhanta, different from Aryabhatiya. Okay. So earlier we had a yuga of 5 years only, short yuga in Vedanga Jyotisha. Later, a Mahayuga, 43,20,000 years come, and according to Aryabhatiya, there are 72 Mahayugas in a Manvantara, and a Kalpa has 14 Manvantaras, which amounts to 1,008 Mahayugas. Within the Mahayuga, there are Kruta, Treta, Dwapara, and Kali. All are quarter yugas of equal duration, 10,80,000 years. Okay, that is the system in Aryabhatiya, but mostly now, okay, in all other texts, Kruta, Treta, Dwapara, and Kali are in the ratio 4:3:2:1. Kali is a shortest, it has got only 43,20,000 divided by 10. So that is 4,32,000. And Dwapara has twice that, Treta has thrice that, and Kruta has 4 times that. And the beginning of the current Kali Yuga is mean sunrise at Ujjain of Friday, February 18, 310 BC. So that is in most other texts also. Why these large units of time? This is very characteristic of India, because all planets make integral number of revolutions around the Earth in a Mahayuga, indeed in a quarter yuga according to Aryabhata. If you include apogees and nodes also, everything will come back to same position after a kalpa. So this is the conception. And Aryabhatiya gives the number of revolutions in the background of stars. Okay, number of revolutions in a Mahayuga, of 43 lakh 20,000. The number of revolutions of sun is 43 lakh 20,000. That is by definition, because a Mahayuga is 43 lakh 20,000 years. Okay, so sun makes this many revolutions in the background of stars. So the sidereal period comes out to be this 365.25868. The modern value is 365.25636. This is sidereal period. The moon, Mercury, Venus, Mars, Jupiter, given all these, how many revolutions they make in one Mahayuga, 43 lakh. Moon is, of course, 5 crore 77 lakhs 53,366. See, so the sidereal period is just 27.33 days. Okay, like that. Other planets also there are close to. Where exactly he gets this, we don't know. I mean, it's possible it has been borrowed. We don't know, but certainly epicycle theories have been borrowed. I will come to that. So this is the number of revolutions. Now what are the mean and true longitudes of planets? See, you got Ahargana, concept of Ahargana, day count for any day. This is the number of days between the beginning of a epoch like Kali Yuga beginning and a given particular day. So the angular position of the planet at any time with respect to a reference line along the ecliptic is called longitude. Okay, here in the figure, this gamma or actually epsilon kind of a thing. So that this is center, you take it as OP, you see. So that is the angle. So that is theta. So the longitude. The mean longitude is something if it is moving uniformly, you call it mean. And reference line is the direction of the beginning point of Mesha Rashi. Okay, so that is Ashwini Nakshatra. Okay, so that is the beginning point of the Mesha Rashi, Ashwini Nakshatra. That is the line, So with respect to that, because if you want to measure an angle, it is with respect to some line. The moon and planets move in planes which are slightly inclined to ecliptic. We ignore this inclination for time being. Assume for the moment that the planets move uniformly with constant speed on circles with Earth at the center in the plane of the ecliptic only. Then this angle is called mean longitude and denoted by theta 0. This varies at a uniform rate. So theta 0 is equal to omega t basically. And in Aryabhatiya, mean longitudes of all planets is 0 at Kali Yuga beginning. So NP denote the number of revolutions of a planet in a Mahayuga, which has dy days. It's called Yuga Savana Dina. Number of days, civil days in a Mahayuga is called Yuga Savana Dina. I should have told you earlier. You see, Yuga Savana Dina is start coming here 1577917500. So these are Yuga Savana Dina. Number of days in a Mahayuga. Okay. See, let NP denote the number of revolutions of planet in a Mahayuga, which is dy days. Then by the rule of 3, the number of revolutions completed by the planet in A days is NP into A by dy. Obviously, in NP days, there are dy days, number of revolutions. NP in A days is A by dy into this. So this will not be an integer in general. Each revolution corresponds to 360 degrees, as you know. And the integral part of NA corresponds to integral multiples of 360 degrees. An angle varies from 0 to 360. So integral part we drop, only the fractional part. So the mean longitude for Ahargana A is NA, fractional part of this into 360. Now the apparent motions of sun, moon and planets in the background of stars are not uniform. 2 corrections are needed to obtain true geocentric longitude. These are Manda and Shigra Samskaras. Manda Samskara arises because of the eccentricity of planet's orbit. It's called equation of center in modern astronomy, positional astronomy. So this is the only correction to sun and major correction to moon. The longitude obtained after this correction is called to longitude, mean longitude is called Mandasputa. For actual planets, there is one more correction. For actual planets, Mandasputa is the true heliocentric longitude, that is with respect to sun. And the Shigra Samskara, this amounts to converting the heliocentric longitude, that is with respect to sun, that is Mandasputas, to geocentric longitude, that is with respect to earth. So in the Aryabhatiya, these two corrections are discussed clearly for the first time in Indian tradition. The epicycle models used in obtaining the two corrections are probably Greek in origin, because there is no clear reference to this in Indian texts. So probably they are Greek in origin, though the details of the models are very different in Greek and Indian traditions. This planetary model described by Aryabhata roughly amounts to planets orbiting around the sun in elliptic orbits, with sun itself orbiting around the earth. But Aryabhata doesn't state it. You see, people sometimes, there are statements which said, oh, Aryabhatiya had a heliocentric model. That is not true. It amounts to the heliocentric model, but he doesn't say. He only gives the details of calculation, how to calculate the planetary position. Some kind of quasi-heliocentric model came later. I will come to that later anyway. That's only in 1500 AD or CE by Nilakanta. I will come to that. But this heliocentric is implicit, not explicitly stated. Now, for all this, trigonometry is needed for calculating this correction. So now we'll come to trigonometry, how it is treated in India. So trigonometry formulated as in India plays a crucial role in algorithmic formula-abundant nature of Siddhantic astronomy. Okay. So in the left figure, there is a circle. See, there's a OD, there's a radius, and extended, you get a diameter. So then OA is there. So the angle between OD and OA is theta. The arc, of course, is r theta, where r is the radius. Then this AB is called Jya, or r sin theta. It's called Jya in India. Okay. And radius is normally taken to be, circumference is 21,600. So the radius is taken to be this by 2 pi 3438 minutes. So for an angle theta or an arc theta, so this is Jya or Jiva, is AB is r sin theta. And OB is r cos theta, is called cotijya or kojya. So the modern sign is essentially the Indian Jya, except for the factor r. Okay. In Indian trigonometry, the Jya, it is a distance, not a ratio. See, in modern trigonometry, sine is opposite side by hypotenuse. Here, it is just the opposite side corresponding to some radius r. Okay, so r sin theta. If sin theta is a modern sign, Indian Jya is r sin theta. R is normally 3438. Okay. Whereas in Greeks had this formula for this way. See, in the right figure, so you have this chord AC, arc AC and chord AC. Okay. So this chord AC is, corresponds to angle 2 theta here. So that is the chord, Greek chord, which is 2r sin theta. See, but here, according to Greek, in the Greek formulation, there is not even a right angle triangle. There is no concept of cosine and all that. And in all calculations, there is the sign that appears. So Indian sign is perfectly suited for writing formulae and calculations. And chord is far less so. Okay, that's an extremely important, fact that Indian sign is what is, the modern sign, and also it is much more suitable for writing formulae. In fact, there are no formulae in Greek astronomy, or European astronomy before some 15th century, 16th century like that. Only Indians have formulas. I'll come to that. So the term sine and cosine can be traced to India. See, Ja is also called Jiva in India. So it was adapted by the Arabs, and there Jiva is became Jiba in Arabic, read as Jab. We also have Jab. You see in Hindi or Kannada and all that, Jab is there. So Jab means a pocket or fold, and translated into Latin as sinus or sine. So ja to sine. So the term sine is derived from the Indian jiva. So it doesn't appear to be so, where is jiva and where is sine. So it doesn't appear to be so. So they are related. So now in India, the complement of the ja is kotijya and sometimes written as koja. So the complement of sine is cosine. So that's a very clear indication it is of Indian origin. You see, koja, kotija, ko. So sine, cosine, they are really, related to Indian formulation of trigonometry. Greeks also had, as I told, but it is much, much more cumbersome. That is a very important thing. And Indian ja is what is accepted by the Arabs everywhere later. And that is what is happened followed modern era. I'll just illustrate suitability of Indian ja for formulae. See, in Indian units, one civil day is 60 nauticas. 24 hours is called 60 nauticas or ghatikas. When the sun is on the equator or equinox, declination is delta is 0, then the duration of the daytime is 30 nauticas. That is, sunrise to sunset is the same as sunset to sunrise. On any other day, this duration depends upon the declination delta and latitude phi. So 6 degrees corresponds to 1 nautica because 60 nautica corresponds to 360 degrees. So the duration of daytime is in this figure. See, the sun rises at A, goes on the top to the meridian, you say, so then comes down. This is W is west, north, south, written. See, corresponding to this, this arc from T to B. So there is the angle TPB. See, that is 90 degrees, or it corresponds to 6 hours or 15 ghatikas. Whereas sun is travel for some more time before setting, this BD. So that is called Chara in India. Chara. Okay. So the duration of the day is 2 into 15 plus 1 by 2 because you have to take the behind. You see behind the meridian above 2 into 15 plus 1 by 6 delta half, where delta alpha is in degrees, ghatikas or chara. So delta alpha is given by in India in this formula, sin inverse, sin phi, sin delta by cos phi, cos delta. Of course, they will not write it like that. They say that take r sin or phi. So that is called the akshajya, multiplied with the krantijya or sin delta, divide by lambajya called r cos alpha, and further divide by jujya, that is cos delta. Okay, then take the arc of this. Okay, so then that is the arc corresponding to Chara. That is how they describe it, but it is exactly the same as this. There is no such expression in Ptolemy's Almagest. The tables after tables for finding the variation of data. Whereas here, this gives the formula for finding duration of daytime for any latitude and for any declination. Okay, so this is the formula. Similarly, for other physical variables, planetary positions, you have the formula. Okay. Indian signs, for finding Indian signs, they normally quadrant is divided into 24 equal parts. Each arc bit corresponds to 90 by 24 or 3 degree 45 minutes or 225 minutes. Then the procedure for finding R sin I alpha. You see, alpha is this. So integral multiple of that R sin I alpha is given. So this is, P1, N1. So this R sin alpha, P2, N2. It is R sin 2 alpha like that. R is 3438. The R sines of the intermediate angles are to be determined by interpolation. They very clearly state it. What is remarkable is Aryabhatiya gives the second order difference equation for R sin I alpha in Aryabhatiya. So it is R sin I plus 1 alpha minus R sin I alpha. So that is the difference. Okay. So then these also a difference. These I plus 1 I, these I plus I minus 1. R sin I alpha minus R sin I minus 1 alpha minus this R sin I alpha by R sin alpha. So the tables of signs are generated from this, which R sin alpha is equal to R alpha is 225, as arc and the half chord will be basically the same. Okay. So without any input, actually you are generating all the signs. So this is very amazing. Aryabhatta realized that second order difference is proportional to R sin this. This is called a difference equation. So as far back as 499 C itself it is there. Second order relation. This equivalent of d squared by dx squared sin x is equal to minus sin x. I mean, apart from one or two constants. You see? So this is some kind of a d by dx. And the difference between this and this, that is the d squared by dx squared. So that is proportional to minus sin x. The exact second order difference equation is given in a text called Tantra Sangraha. It is not this, last term is not this, but last term is this. So the actual value of this is 0.0042822. Aryabhatiya gives a rough figure. So this one. Whereas Tantra Sangraha approximates this to this 0.042827. So this is the how they generate the. And so you have a tables expressed in Shloka. So Aryabhatiya and later Madhava, modern value. So you are getting the sine table. They give you the sine table. Okay. So theta in minutes. So if you want to get it in degrees, you have to divide by 60. And this is the value, Madhava value for the sine of, let us say, 225 minutes or 3 degree 45 minutes. And this means that 3438 into r sine of 3 degree 45 minutes is equal to 224 plus hexadecimal units, 224 plus 50 by 60 plus 22 by 3600. So that's the meaning of this, if you write like this. And the sign of intermediate angles is by interpolation. Now, as I told you, you have to have a model for finding the correction because the orbit is not circular, it is eccentric. We know that it is elliptical. Okay. So here, Manda Samskara. So it is, see, mean planet P0 moves at a uniform rate on the circle, red dash circle. The center Earth is O, okay? And you draw a small circle around P0 and draw a line parallel to this called, this line OA in the direction of what is known as upside, in the direction of the Mandocha, as it's called in this thing. So then this is the true position. So gamma OP is the true longitude, that is the longitude with correction. Alternately, you say that the planet moves uniformly not with respect to O, center of Earth, but with respect to some other point in a direction called Mandocha or apogee. And then, so it is called a Pratimandala. So dark circle, full circle, you see, solid circle, that is called a Pratimandala or Graha Vrutta. The dash circle, that is called the Kaksha Vrutta. So this is the point planet P. So the planet will be like this. Either you have this epicycle like this or a eccentric circle like this. So this is the conception, and one can find out the thing. So one can show that this gamma OP0, that is theta 0, mean longitude. Gamma OP is the Mandasputa. Okay, correction with correction. Then this is R sin theta 0 minus A, R by K, this, where theta 0 is the mean longitude. We can find out immediately. Theta is the longitude of the apogee. So this is the formula. In most Indian texts, R is not a constant, but varies as R by K is R0 by R, the constant. So it is like this, sine inverse R0 by R, sine of theta 0 minus theta A. So if we take this R0 by R is small, so Mandasputa minus this is minus R0 by R, sine theta 0 minus theta. So this is the difference between mean longitude and what is called the Mandasputa. If you compare with the expression for the equation of center in Kepler's model, equation of center is difference is this. Kepler model, we are all familiar, physics everybody knows. Okay, the planet is moving in an ellipse with sun as one of the focus, right? So suppose theta h is the longitude with respect to some line, and theta 0 is the mean longitude, then theta h minus theta 0 is minus 2e into sine theta 0 minus theta a, where theta a corresponds to this line A, apogee. Okay, so the formula are the same. E is called eccentricity of the ellipse. We know that, ellipse has eccentricity and all that. So Indian model is give the same result as elliptical Kepler model to first order in E. If you go to higher order, of course, there will be difference. But E is small, so it is more or less correct. So theta ms, so that is the Mandasputa can be identified with heliocentric longitude and R0 by R with 2. Then Shigra Samskara called the conversion from heliocentric to geocentric. I will not go into deriving this. See, I'm just explaining the figure. See, Earth is here. You see, E. Then S is the position of the sun. S is the position of the sun. Okay. So that is some angle which is called Shigrocha. Okay. So now the planet is moving with respect to the sun. Okay. It is moving in a circle or eccentric circle with respect to the sun. Okay. So that is theta ms, gamma sp. So that is the heliocentric longitude. But we want to convert it into geocentric longitude. So what we need is gamma ep. Okay. So then that is the, with respect to Earth, geocentric longitude is theta. So theta minus theta ms. So theta is the geocentric, theta ms is the heliocentric longitude. This depends, this is the formula for this. Rs by R is essentially Rs is the sun-earth distance and capital R is the planet or sun distance. So this is what it is. But Indians don't say that it is sun-earth or sun planet or earth sun. They say this is the parameter. There's a small circle, there's a big circle of radius Rs by R and all that kind of a thing. But this is the geometrical model. In Kepler model also you can easily get this. This is the exact formula. So it has the same kind of a dependence. So if you compare them, you see the Indian formula is this, sine theta minus theta m. Oh, the first one. The second one, Kepler formula is this. The formula for theta in Indian text is exactly the same as the one given in equation which follows from Kepler model for an exterior planet. For interior planet, the treatment is slightly different. When the Mandasputa is identified with the heliocentric longitude, true longitude, and Rs by R in the former, the Indian model is identified with R by R in the Kepler model. Okay, so they correspond to actual distances. Rs by R is the geometrical, quantities. related to radii of different circles. So they have the same formula. Okay, that is why it works. In fact, it will give the same results basically if this RS by R Indian and R by R modern can be compared. So I repeat that the Indian values, Aryabhatiya value, RS by R and all that, this is the planet Sun divided by planet Earth for interior planets Mercury, Venus, and Sun Earth and the ratio of Sun Earth and planet Sun for the Mars, Jupiter, and Saturn. So this is the parameters in Indian astronomy for the geometrical model, whereas in Kepler model there are the actual distances, modern these things, but there is a correspondence. So it gives the correct result. Okay, it captures the Kepler model. You see, way back, even 1500 years back, the Kepler model is somewhat implicit in Indian model. So that is what is very important. You see. Okay. So the agreement between the two sets is very remarkable, but it's true for Ptolemy's procedure also, but more complicated in Ptolemy's procedure. You see, computations wise also. So this is how Indian model work. Okay, I repeat that a geometrical model in which there's one Shigrocha, Mandocha, Kaksha Vrutta, etc., and calculated the positions, and it gives the same results as the Kepler model. I'm telling you, I will come to that why I'm, uh, comparing this Kepler model rather than Newton and afterwards. That is because, you see, Kepler also didn't have the concept of force and, F is equal to ma and all that. It's all kinematical model, not a dynamical model. There is no dynamics. So Newton afterwards is all dynamics. Okay, so without the concept of force, acceleration and all that, both Indians, Greeks, everywhere, they used to could, calculate positions of planets. You see, they could without this concept. That's very important. Only afterwards one can, came this force and gravitation law and all that. So without all this, we could find out very accurately, and Indians gave the correct decision. Yeah, now I don't have too much time. So I'll just give some major texts, Aryabhatiya, then Varaha Mihira's Panchasiddhantika, Bhaskara 1, Aryabhatiya Bhashya, Mahabhaskariya, etc. Brahmagupta Yuda, Brahmasputa Siddhanta, Kandakadyaka. So very great works. Lalla, Shishyadi Uddita Tantra, Vateshwara, Manjulacharya, Sripati, then the great Bhaskaracharya too. You all would have heard of Siddhanta Shiromani, Leelavati, Bija Ganita and all that. And he talks of instantaneous velocity of planets. The concept of derivative is there in some manner. In area of integration is there. So that is what is there in Bhaskaracharya. I don't have the time for those. And post-Bhaskara developments in Kerala, you have Madhava, Parameshwara, Nilakanta Somayaji, and so on. So according to Nilakanta Somayaji, according to the major division of the traditional planetary theory by Nilakanta Somayaji in Tantra Sangraha, he gives this model: planets move in eccentric orbits. That is not in the circle, the center is different around the sun, and which itself moves around the earth. Okay, so they move in eccentric orbits around the sun, and the whole sun and the whole planets move around the earth. So this is essentially the Tycho Brahe model, and Neelakanta's model is 1500 CE, before Copernicus and before Tycho Brahe 1580. You see, so he had this. You can say he had a quasi-heliocentric model. So there is a significant advance in spherical astronomy and all that in this text. And you have this Ganita Yukti Bhasha by Jeshta Deva. They give infinite series for pi, sine, cosine, etc. and so on. You see. So there are other places, persons also, after Bhaskara, Ganesha Daivagna, important persons called Chandrasekhar Samanta in Odisha. He gave a very big book called Siddhanta Darpana. Then Surya Siddhanta, which is very important and popular. So these are all the various texts. Okay. So, sorry, I don't have too much time for this. Just I will say that apart from planetary models, there are ways how to calculate longitude. For instance, from the noon shadow, one can find out the declination of the sun and latitude of the place, okay, by finding out the noon shadow. You see? So if the shadow is that of a 12-inch gnomon, Adashankala Shanku OY, so that will be 12 sin Z, sin Z. It will be actually shadow 12 tan Z0, which is the noon shadow at the exact noon, true noon. So then, from that, if you have to, as you measure this, you can find out the Z0, and Z0 is 5 plus or minus delta declination. So from that, the declination of sun can be known, and from the declination, the longitude of sun can be known, and so on. And latitude can be found from other ways also. You see, you can find it. Professor Kagali was mentioning how declination and latitude can be found. Yeah, he has got a method. So this can be compared with that. This is an interesting thing. So to summarize, is the time to summarize. So there's astronomy in Veda, Vedanga and all that. Then Siddhanta period from Aryabhatiya onwards. Mahayuga 43,20,000 years. For all this, trigonometry is needed. So modern trigonometry is basically Indian in origin. So methods to compute Jya, that is sine, cosine and all that. The planetary models give same results as Kepler model, Nilakanta Somayaji's quasi-heliocentric model, and I have also mentioned the major astronomers. So, but it is all algorithmic in nature. They use the rules and the explanations are in commentaries. And it is an evolving tradition, constant updating of parameters. Concepts also are sometimes modified. There's a flexibility of approach. So new ideas can be accommodated. See, according to many people, Indians were very rigid. You see, they just, went by tradition. That is not true. They, of course, followed tradition as much as possible. But like in science, if you have to change something, it will be changed to account for observations. There is a steady improvement in mathematics. And for all these, not only text, commentaries are also you should read. That's what we have done. We have done our work on Bhaskaracharya Siddhanta Chiromani. We have gone through the detailed commentary, his own commentary. We have translated it, so that we will know what is Bhaskara's thinking. See, not, what we attribute something and all that, oh, Bhaskara said this, Bhaskara said that. What did he say in his own words? How did he say? What is his method according to him? What is science according to him? That all comes when you read the commentary, his own commentary. So that is what is important. One should be truthful. One should, of course, respect our tradition, go through the traditions, but certainly should be only authentic things we should, propagate. Not, black holes were there in India, things like that. You see. So dark matter was there and black, various things like that. To see what is there in the text and try to understand them. Thanks a lot for very patient hearing. Thanks a lot.
Thank you very much, Professor Sriram, for a very nice introduction to Indian astronomy.
Yeah.
Now there is time for some questions. Would you like to answer some questions if there are any?
So,
okay, some questions are now welcome. Anybody would like to ask any questions?
Amen.
Yeah, please ask.
Sorry, 1 minute I have to. Yeah.
Sir, you know,
Sorry.
one simple question.
No, I'm back.
It's okay, sir. I have one simple question.
Yes, I'm back, sir.
That's okay. We don't need your one question is, what about the instrument they were using? Is there any record of the astronomical unit
Sorry, 1 minute.
instruments they were using, and especially with regard to time?
1 minute, 1 minute. 1 minute.
Oh, some breakup, huh?
Where is the? Sorry.
At least you answer by no video required. Just
1 minute, 1 minute. I'm coming.
uh,
Yeah.
question ಏನಂದ್ರೆ, are you able to hear me?
Hello. Sorry.
Can you hear me?
ಏನೋ ಪ್ರಾಬ್ಲಮ್ ಆಗಿದೆ, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? ಹಲೋ,
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. ಅವ್ರದ್ದೇನು ಕಟ್ ಆಗ್ಬಿಡ್ತಾನೆ, ಅದು ಲಿಂಕ್ ಕಟ್ ಆಗ್ಬಿಡ್ತದೆ ಕಾಣ.
ಏನೋ ಕಟ್ ಆಗಿದೆ.
ಹಾ, ನಂದು ಪ್ರಾಬ್ಲಮ್ ಆಯ್ತು ಇಲ್ಲಿ ಡೆಸ್ಕ್ಟಾಪ್.
ಹೌದು, ಏನೋ ಸ್ವಲ್ಪ ಸಮಸ್ಯೆ ಆಗಿದೆ, ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಸರಿಯಾಗಿ.
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ. ನಿಮ್ದು ಕೇಳಿಸ್ತಾ ಇದೆ, ಬಟ್ ಅವ್ರು ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
ನೆಟ್ವರ್ಕ್ ಎರರ್ ಇದೆ, ಅವ್ರು ಎಕ್ಸಿಟ್ ಆಗಿಲ್ಲ, ಬರ್ತಾರೆ.
ಅಲ್ಲ, ಏನೋ ಹೋಸ್ಟ್
ಫೈಲ್ ಶೇರಿಂಗ್ ಪ್ರಾಬ್ಲಮ್ ಆಗುತ್ತೆ. ಫೈಲ್ ಶೇರಿಂಗ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಮತ್ತೆ ಅವರು ಪರ್ಮಿಷನ್
I can hear. Yeah.
My question is,
Yes.
you have any record
I
of
can hear. I can hear.
astronomical instruments they were using in those days, especially with regard to time and so on, angle measurement to time measurement? So, are the instruments available? Record of the instruments available? I think he's not able to hear. Hello? So, Sriram, I think he cut out the signal.
ಆಗ್ಲೇ ಅವರೇ, ನಿಮ್ಮ ವಾಯ್ಸು ಭಾರಿ ಫೇಂಟ್ ಆಗೋಗ್ಬಿಟ್ಟಿದೆ.
ಹೌದು ಸರ್, ನಿಮ್ದು ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
ಡೆಸ್ಕ್ಟಾಪ್ ಕಟ್ ಆಗ್ಬಿಟ್ಟಿದೆ, ಪ್ರಾಬ್ಲಮ್ ಆಗಿದೆ. ಐ ಆಮ್ ಯೂಸಿಂಗ್ ಮೈ ಫೋನ್.
ಲೆಫ್ಟ್ ದಿ ಮೀಟಿಂಗ್ ಅಂತ ಏನೋ ಬಂತು.
ಇವಾಗ ಈ ಮೊಬೈಲ್ ಅಲ್ಲಿ ಇನ್ನೂ ಸ್ವಲ್ಪ ಚೆನ್ನಾಗಿ ಬರುತ್ತೆ. ಐ ಕಾಂಟ್ ಶೇರ್ ದ ಸ್ಕ್ರೀನ್.
ಮಾಡ್ತಾ ಇದೀನಿ, ಅದು
ಓಕೆ. ನಂಗೆ ಕೇಳಿಸ್ತಾ ಇದೆ. ಕ್ಯಾನ್ ಯು ಹಿಯರ್? ಎಸ್. ವೆರಿ ಗುಡ್, ವೆರಿ ಗುಡ್.
Record of astronomical instruments which were used in those days, especially with regard to time, angle measurements. So, idya anta.
Angle measurements ಎಲ್ಲ ಇದೆ. So there is, this there is observatories in, Ujjain, in Jaipur. Jaipur it is there, but they are all little more recent. But older instruments are also there. How to measure the azimuth and all that. How to measure time. How to relate time with shadow. Author of the instruments. So for time, this clepsydra and that kind of instruments are there. But for angle and all that, what is there in these jantar mantras and all that, so that clearly tell you how to measure the angle.
There are more recent. I'm talking about Aryabhatta time.
Aryabhatta time, though, it is not there, but but in this instruments descriptions are there in Brahma Sputa Siddhanta. Even some Aryabhatta, I think some few instruments are there. And many other these things. Yantradhyaya, then Bhaskara Shiromani. He does talk about yantras. Like sundials, horizontal, I mean the equatorial sundial, and for measuring angle, definitely they are there.
Any other questions?
Sir, can I have a question?
Please.
Sir, Professor Vijay Kumar Todmani from Bangalore University, sir.
Yeah.
Sir, firstly, I thank you very much. So very much resourceful and quite interesting. And I teach astrophysics and this all these things, sir. So I have a small query. that in the perturbation of the coordinates of the all the celestial objects,
Yeah.
be it objects in solar system or star or whatever. So the nutation phenomena, can you elaborate on the precision and nutation? Those two corrections will add to the coordinates of the objects, celestial objects.
Yeah.
Yeah, this is over 50 years epoch, like 1950, 2000, things like that it goes. The almanacs or for corrections are added for the 50 years period. Can you just
Yeah.
elaborate on the notation component of the perturbation of the coordinate?
No, I'll tell you. No, no. Nutation was not there. Nutation is, tilt of Earth's axis. Tilt itself varies.
Yes,
So
sir.
tilt is taken to be nearly 24 degrees in India. Okay. Tilt is the same.
Yes, sir.
Okay. But precision is very much there. Hello?
Okay, sir. Yes, sir.
Can
Yes,
you
sir.
hear? Precision is everywhere. Bhaskara mentions, that precision should be taken into account. See, I wrote
Yes, sir.
sine delta is sine epsilon, sine lambda. I wrote, right?
Hmm.
So delta is declination, epsilon is the opacity of ecliptic, and lambda is the longitude. See, this longitude has to be with respect to equinox for this formula. You see, for this formula, lambda is the tropical longitude. So, when Bhaskara says, whenever you have deal with these kinds of things, declination, time, and called Prashna problems, you have to add the precision, and he will tell you what is the. And he says you calculate according to Siddhantas, and for the longitudes you have to add 11 degrees at each time, 11 degrees. So you have to add the 11 degrees to get the tropical longitude. Yes, they had this.
Question?
The civilian day of 24 hours, sir.
Sorry?
Civilian day of 24 hours, which is exactly 24 hours. It is a fictitious day, no, sir. It doesn't really refer to the exact the time interval of the day over the years and all. It is fictitious in my opinion. 24 hours. What we practice for the calendar.
No, 24 hours is the average time period. 24 hours is the average time period, okay, which is called 60 ghatikas. Indians didn't use hours, 60 ghatikas, but they say that it is average. But it is because of the chara, because of the declination, the duration. And apart from that, a motion of sun in the background of stars, because of the duration will change. They say it very clearly.
Okay.
One small another
Sir,
question.
do you have your own work book for comparison of all these things? I would like to refer to your books.
See, I have got one old this thing book, which is somewhat elementary. I'm writing the book, more. See, elementary school level book, but it is. I want to edit it, but it is available now. I can send it to you, no problem.
So I'll contact you later, sir, for inviting you to Bangalore.
My email address.
I will
See,
give
my
you his
email address.
You can contact him. Okay.
Yeah. See, please, Professor Kagale, you can share our email address.
Yeah,
so
I
can
will share your
whatever
email.
is.
I'll share your email with them. Okay.
Email
Thank
address,
you
so I
very
can
much,
definitely contact. I can give you some, material.
Thank you, sir.
Happy to see Umesh Rao.
Sir, good morning, sir.
ತುಂಬಾ ದಿನ ಆಯ್ತು ನಿಮ್ಮನ್ನು ನೋಡಿ. ಹೇಗಿದ್ದೀರಾ?
Umesh from Mysore.
ಚೆನ್ನಾಗಿದ್ದೀನಿ, sir.
Yes.
I'm in Mysore, sir.
Oh, Mysore, okay.
Please come this side, sir, sometime.
ಬಂದಿದೆ. I had come in February.
ಈ ಸಲ ಬಂದಾಗ ತಿಳಿಸಿ, sir. I will correspond with you on the email.
Yeah. See, there's one Vidyavartaka Sangha that organized this thing, faculty development program, some short-term course. Eurasena Power Sena,
Yes, sir. Yes.
So here organized. What is his name?
In Vidyavardhaka.
He is not in Vidyavartaka, but he was organized that for them. Our hesaru.
Anyway, don't worry about that.
Yeah.
I had a small question.
Ashok Rao.
Ashok Rao, yes. I know Ashok Rao, sir.
Okay, Ashok. He had invited me. I had come. Yeah. So Mysore Lily.
Sir, I have one question.
Yeah.
Our solar system moves in the Milky Way galaxy also. It is set to. So, will that make any changes in the calculation, sir?
Not only minute changes that they don't consider at all. You see, that is only small amount. You see, these all these are all. There is no other motion. There is no proper motion, right? What is called proper motion. Yeah, proper motion is not considered. Yeah, but there is only small amount.
Right.
Yeah.
Namaskara, Professor Sriram avare.
Namaskara. Oh, Sudha Chennai. Very happy to hear your voice. Yeah.
ನನ್ನ ಈ ವಿಡಿಯೋ ಸ್ವಲ್ಪ ಕಾಣಿಸಲ್ಲ, ಅದು ನನ್ನ ಮನೆಯಲ್ಲಿದ್ರೆ ಇಂಟರ್ನೆಟ್ ತುಂಬಾ ಸ್ಟೇಬಲ್ ಇಲ್ಲ, ಹಾಗಾಗಿ ಮಾತಾಡಿದ್ ಕೇಳಿಸ್ತಾ ಇರೋದೇ ದೊಡ್ಡ ಸಂತೋಷ ನನಗೆ. ಮಾತನ್ನ ಕೇಳ್ಬಿಟ್ಟು ಮತ್ತೆ ಅಂತ.
Okay, sir. Glad to hear you again.
ನನಗೆ ಒಂದ್ ಸಣ್ಣ ಪ್ರಶ್ನೆ ಕೂಡ ಇತ್ತು, ಅದನ್ನ
ಹೇಳಿ.
ಯುಗ ಅನ್ನುವಂಥದ್ದು 5 ವರ್ಷ ಅಂತ ಹೇಳ್ತೀರಾ, ಮಹಾಯುಗ ಅನ್ನುವಂಥದ್ದು ಇಟ್ ಈಸ್ ಸಚ್ ಎ ಗ್ಯಾಪ್. ಯುಗ ಅನ್ನುವಂಥದ್ದು ನಮ್ಮ ಕಲ್ಪನೆಯಲ್ಲಿ ಲೈಕ್ ನಾವು ಕಲಿಯುಗ, ತ್ರೇತಾಯುಗ, ದ್ವಾಪರ ಯುಗ ಅಂತ ಹೇಳ್ಬೇಕಾದ್ರೆ ನಮ್ಗೆ ವರ್ಷಗಳ ಕಲ್ಪನೆ ತುಂಬಾ ದೊಡ್ಡದು ಅಂತ. ಯುಗ ಅನ್ನುವಂಥದ್ದನ್ನ 5 ವರ್ಷ ಅಂತ ನೀವ್ ಹೇಳ್ಬೇಕಾದ್ರೆ ನನಗೆ ಸ್ವಲ್ಪ ಲೈಕ್ ವಾಟ್ ಡು ಯು ಮೀನ್ ಬೈ ದ ಇಯರ್ಸ್ ದೇರ್ ಅಂತ.
ಇಲ್ಲ, ಅದು ಹಳೇದು. ಯಜುರ್ವೇದ, ವೇದಾಂಗ ಜ್ಯೋತಿಷ, 5-year ಯುಗ, ಶಾರ್ಟ್ ಯುಗ. ಮಹಾಯುಗದ ಕಲ್ಪನೆ ಇಲ್ಲ. ತುಂಬಾ ಹಿಂದೆ ವೇದಿಕ್ ಟೈಮಲ್ಲಿ ಮಹಾಯುಗದ ಕಲ್ಪನೆ ಇಲ್ಲ. ಆಮೇಲೆ ಯಾವಾಗ್ಲೂ ಬಂತು. We don't know. Certainly before Aryabhatiya, maybe some 1000 BC or 600 BC or something. ಆವಾಗ ಮಹಾಯುಗದ ಕಲ್ಪನೆ ಬಂತು ಅಂತ ಕಾಣುತ್ತೆ. ಆಮೇಲೆ of course Aryabhata uses this for this, Yeah. The whole thing changes, more accurate calculations.
Okay. ಅದು 4:3:2:1 ಅಂತ ಹೇಳಿದ್ರಲ್ಲ, ಅದು ಮಹಾಯುಗಕ್ಕೆ ಅಲ್ವಾ ನೀವು ಹೇಳಿರುವ?
ಹೌದು, ಮಹಾಯುಗಕ್ಕೆ.
Yeah, thank you. Very
You're
nice.
welcome. Thank you.
ಒಂದೇ ಒಂದು ಸ್ಮಾಲ್ ಕ್ವೆಶ್ಚನ್ ಇದೆ. ನೀವು ಚಂದ್ರಶೇಖರ್ ಸಾಮಂತ ಬಗ್ಗೆ ಹೇಳ್ದಲ್ಲ, ಚಂದ್ರಶೇಖರ್ ಸಾಮಂತ ಒರಿಸ್ಸಾ.
ಹೌದು.
ಅವ್ರದ್ದು ರಿಸಲ್ಟ್ಸ್ ಎಲ್ಲ ತುಂಬಾ ಅಕ್ಯುರೇಟ್ ಆಗಿದೆ ಅಂತ ಕೇಳಿದೆ. ಬಹಳ ಅಕ್ಯುರೇಟ್ ಆಗಿದೆ. ಹಿ ಮೇಡ್ ಅಬ್ಸರ್ವೇಷನ್ಸ್ ಅಂಡ್ ಥಿಯರಿ. ಅವ್ರ ಸಿದ್ಧಾಂತ ಏನೋ ಯಾವ ಶಿರೋಮಣಿನ ಏನೋ ಬುಕ್ ಬರೆದಾರಲ್ಲ, ಅದರ ಬಗ್ಗೆ ಯಾರಾದ್ರೂ ಸ್ಟಡಿ ಮಾಡಿದಾರ ಫರ್ದರ್?
See, there is one book, okay, which is not there is one translation also, okay, but ಅದು ತುಂಬಾ ಸಮರ್ಪಕವಾಗಿಲ್ಲ. It is not that good, this thing, okay, but there is one book which is a seminar I also attended about 20 years back or so, okay, so summarizing what he says, but that is available. If there is there, I will see. If it is there, I can send it to you, no problem. Soft copy idre I can send it immediately.
ಅವರೆಲ್ಲ ಡೀಟೇಲ್ 20-30 ವರ್ಷ ಅಬ್ಸರ್ವ್ ಮಾಡಿಬಿಟ್ಟು he has recorded his observations and
see Professor see Professor Kagli is mentioning observations of Samanta. See, it's very, very significant. That is in 1860 or so. He has devised his own instruments. And then make some these things, measurements regarding sun, moon, and planets and all that. But one thing is, he might be familiar with modern astronomy. At that time already modern European astronomy was there, and he was a very brilliant person. But of course he didn't know English and all that, but maybe he had some effort. In fact, he says, that this heliocentric model in Europe, he talks about it. So he knew about it. How much he knows, we don't know, but he was aware of it and using it. But Even then, he has done everything in the Siddhantic framework. So that is what is important.
Okay, thank you. Professor Nagaraj
So
wants to
it can be considered as the last great Siddhanta in Indian tradition. Siddhanta
ನಾನು
Darpana.
ನಾಗರಾಜ್ ಅಂತ ಒಂದ್ ಪ್ರಶ್ನೆ ಕೇಳ್ಬೇಕು ಅಂತ ಇದ್ದೀನಿ. ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ.
ಸರ್, ಈಗ ನಾವು ಸೈಡೀರಿಯಲ್ ಹೇಳಿದ್ರಿ ತಾವು. ಸಿನಾಡಿಕ್ ಪೀರಿಯಡ್ ಅಂತ ಕೂಡ ಈಗ ಮೆಜರ್ ಮಾಡ್ತೀವಿ, ಅಂದ್ರೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ಈ ಸನ್ ಸ್ಪಾಟ್ ಅಂದ್ರೆ ಸೋಹಾನ್ ಸ್ಯಾಟಲೈಟ್ ಇಂದ ಈ ಮೋಷನ್ ಆಫ್ ದಿ, ಹಾಗೆ ನಮ್ಮ ಇಂಡಿಯನ್ ಅಸ್ಟ್ರಾನಮಿನಲ್ಲಿ ಇಲ್ವಾ ಸರ್ ಅದು ಸಿನಾಡಿಕ್ ಪೀರಿಯಡ್ ಅನ್ನೋದು?
Synodic period is there, more or less it is there, because synodic period essentially, see, that is essentially, you know, like see, this lunar month is essentially synodic month. That is conjunction between sun and moon. Okay, and successive time interval. So similarly, synodic period, okay, of any planet is the relative, relative to sun and this thing, successive conjunctions of planet with
successive, yes sir,
with sun. Howdo, opposition or conjunction. So synodic period is a grahayuti inta adalli ಮಾಡ್ತಾರೆ synodic period. Yeah.
ಹಾಗೆ ಸರ್, ಇನ್ನೊಂದು ಡೌಟ್ ಏನು ಅಂದ್ರೆ, ಈಗ ಮಕರ ಸಂಕ್ರಾಂತಿನ January 15th ಅಥವಾ 14th ಆಗ್ತಾ ಇದೆ, ಆದ್ರೆ ಸಂಕ್ರಮಣ December 21st ಆಗ್ತಾ ಇದೆ ಅಂತೆಲ್ಲ, ಇದ್ರ ಪ್ರಕಾರ ಏನು ನಮ್ಮ ಇಂಡಿಯನ್ ಆಸ್ಟ್ರಾನಮಿನಲ್ಲಿ ಏನು ಚೇಂಜ್ ಆಗ್ತಾ ಇಲ್ವಾ? ಅದು ಅಸಲಿ ನಾನು ಈ
I'll tell you. See, there is a lot of confusion. It's good that you ask this question. ಇವಾಗ ಮಕರ ಸಂಕ್ರಾಂತಿ ಅನ್ನೋದು, when sun is 270 degrees, makara, Indian makara, see, Indian mesha rashi beginning it is about 24 degrees from equinox. So equinox, so March, sun comes to equinox on March 21st, and April 21 he comes to beginning point of mesha. Okay, so Indian more or less they talked about this thing only, this mesha, Vrishabha, that kind of thing, with respect to Indian 0 point. But actually they knew that it is not this thing, the winter solstice. They knew that for winter solstice they have to add the ಅಯನಾಂಶ. ಸೊ ಅದು ಅಯನಾಂಶ ಆಡ್ ಮಾಡಬೇಕು. ಬಟ್ ಲೇಟರ್ ಇವಾಗೆಲ್ಲ there is too much of confusion. So I can say that January 14th is Makara Sankranti, but it is not Uttarayana. Uttarayana Punyakala alla. Uttarayana Punyakala December 21st. So sun goes north. So from the lowest point on December 21st to highest, south to north on June 21st. So this is Uttarayana. Uttarayana starts on December 21st. And Makara Sankranti starts on Vishuvat, these are my March 21st. And Makara Sankranti, Mesha Sankranti is on April 14th. And Makara Sankranti is January 14th. So ಅದ್ರ ಅವ್ರಿಗೆ ಏನು ಡೌಟ್ ಇಲ್ಲ. ಬಟ್ ಆ ಹಳೆ ಅವ್ರು ಏನ್ ಹೇಳ್ತಾರೆ, ಭಾಸ್ಕರ ಏನ್ ಹೇಳ್ತಾರೆ ಅದನ್ನ ಸ್ವಲ್ಪ ಸರಿಯಾಗಿ ತಿಳ್ಕೊಳ್ಳಿ. ಈಗಿನ ಎಷ್ಟೋ ಜನ ಪಂಚಾಂಗ ಮಾಡೋರು ಮಕರ ಸಂಕ್ರಾಂತಿ ಉತ್ತರಾಯಣ ಅಂತ ಹೇಳ್ತಾರೆ. Even according to Indians, Makara Sankranti is not